12b. Periodic motion and the pendulum. 12.5. Historical Overview. The origin of the pendulum is unclear. There is evidence in cave paintings that pendulums were used in some occult way to douse for water. The pendulum was a mystery to the ancient Greeks because it defied the notion that a heavy weight would single-mindedly seek its natural place at the center of the earth. To have a weight on a rope continuously swing up and down in an arc did not fit with Aristotle's natural order of things. It was not until the 16th century that the pendulum was first scientifically investigated by Galileo Galilei. Although educated in Aristotelian science, he concluded early in his life as a scientist that much of what he had learned was often contradicted by simple observation. For example, while still a student, he observed in the cathedral at Pisa, Italy, that the periods of swinging chandeliers having equal-length chains were independent of the amplitudes of their swings. This was an important discovery that eventually led to research in pendulum regulators for clocks. The periods of both pendulums and spring mass systems in simple harmonic motion are independent of the amplitudes of their initial displacements. In this section, we will investigate the properties of pendulums and how they approximate simple harmonic motion. 12.6. Description of pendulum motion. A simple or ideal pendulum consists of a mass suspended from an ideal string or a massless rod of length L, called the pendulum arm. All of the pendulum's mass, m, is assumed to reside at a point at a distance L from the point of suspension. Therefore, for an ideal pendulum, L equals L. In this section, the symbol L specifically means the distance between the pendulum's pivot point and its center of mass. When a pendulum swings, its center of mass follows an arc of a circle with radius L. The need to emphasize this point will be clear at the end of this section when we discuss physical, non-ideal pendulums. The forces acting on a pendulum at rest are its weight, mg, and the tension in the pendulum arm, Tp. When the pendulum is hanging still, these two forces are in equilibrium. This hanging position is the equilibrium position for a pendulum. Suppose an experimenter pulls the pendulum to the side so that the pendulum arm makes an angle with its equilibrium position. At the instant he releases it, the only forces acting on the mass are still just the weight of the mass and tension in the arm. 12.7. Pendulum restoring force. What is the restoring force that causes the pendulum to return to its original equilibrium position? The only freedom of movement that the pendulum mass has is tangential along a circular path of radius L. What force acts in a tangential direction? The weight of the pendulum mass is always directed vertically downward. Therefore, weight alone cannot move the mass back to its equilibrium position. If the string were cut, the pendulum could only move downward. The tension applied by the pendulum arm on the mass is oriented radially along the arm, so it cannot cause tangential motion by itself either. Only the sum of these two forces acting at an angle forms the restoring force that returns the pendulum to its equilibrium position. At rest, the tension in the pendulum arm, Tp, is due only to the weight exerted by the pendulum mass. We will designate this tension vector Tp. It is nothing more than the reaction force to the component of the weight of the mass acting in line with the pendulum arm, Tw. The vector Tw is equal in magnitude and opposite in direction to Tp, according to the definition of third law force pairs. See Figure 12.9. The magnitude of this component is Tw equals absolute value of mg times cosine theta. The other component of the pendulum's weight is perpendicular to Tw. This is the component of weight tangent to the circular path. Its magnitude is calculated by Chuck mg sin theta. This is the force that produces the tangential acceleration responsible for the motion of the pendulum. We will call this vector sum the restoring force, Fr, because it is the net force sum on the pendulum mass. Far g shear mge sin theta 12.7. At the instant of release, the tangential or restoring force is equal to the vector sum of the pendulum tension vector, Tp, and the weight vector, mg. The vector equation defining the restoring force is Fr equals Tp plus mg. We will see shortly that this force does not even approximate the simple harmonic motion restoring force except under certain conditions. After it is released, the pendulum accelerates as it falls toward its equilibrium position. Several interesting things happen. As the pendulum's tangential speed increases, it is being accelerated toward the center of its circular path according to the principles of circular motion. The centripetal force Fa that causes this centripetal acceleration is added to the tension in the pendulum arm, supporting the weight of the mass. In equation form, Tp equals Tv plus Fa, where Tv equals Tw equals absolute value of mg times cosine theta, and Fa equals mvt squared divided by L. The vector sum of Tp and mg is no longer tangent to the pendulum path, but tends to rotate toward its interior. See Figure 12.10. Just as Newton's second law predicts, the acceleration of a pendulum is directly proportional to the net force acting on the pendulum mass. The tangential acceleration vector, a sub t, and the centripetal acceleration, a sub c, sum together to yield the total acceleration, a subtotal of the pendulum mass. The total acceleration vector points into the interior of the circular path ahead of the system's radial position vector. If the system is accelerating, and behind the position vector if the system is slowing. The force that causes this total acceleration is the pendulum's restoring force. Tangential acceleration decreases to zero as the pendulum reaches the bottom of its arc, because the tangential component of gravitational acceleration disappears at the equilibrium position. As the pendulum rises in the second half of its swing, tangential acceleration begins to increase in the opposite direction to reduce tangential speed. The total acceleration vector points behind the pendulum, indicating that the vector sum of total tension and weight, the restoring force, acts in the same direction. Examine figures 12-10 and 12-11 to see how this interplay of forces and accelerations controls a pendulum's movement. It should be evident that the force restoring a pendulum to its equilibrium position is not proportional to the magnitude of the pendulum's displacement, nor does it act in the opposite direction to the displacement. So it seems that a pendulum's motion does not conform to the rules for simple harmonic motion. You can see that as the pendulum's initial displacement, its amplitude, from its vertical equilibrium position increases, the tangential speed at the bottom of its swing increases. Centripetal force on an orbiting object is proportional to the square of its tangential speed, so the restoring force on the pendulum is significantly affected by its speed, much more so than by its displacement for large initial angles. Th greater than pi over 8 radians or more than 22.5 degrees, 12.8 small amplitude pendulum motion. If we consider a pendulum starting its swing from a small displacement angle, theta, less than pi over 8 radians from the vertical, then we can make some helpful approximations to analyze the periodic motion of a pendulum. With small initial displacement angles, the pendulum does not fall very far before it reaches its equilibrium position, nor does it acquire any appreciable tangential speed during its swing. Thus, the restoring force is negligible, and tension force in the pendulum arm is essentially dependent only on the weight of the mass and the displacement angle. The restoring force acting on the pendulum is then equal to the vector sum of just the pendulum arm tension and the pendulum's weight. The restoring force vector is also essentially parallel to the displacement of the pendulum mass from equilibrium, a key requirement for simple harmonic motion. The magnitude of the pendulum's initial perpendicular displacement, d, is the length of the side opposite to the initial angle theta in the right triangle formed by the pendulum arm L and the vertical. You can see that d equals L sin theta. The semi-arc length of the pendulum's path, d half the pendulum swing, is d equals r theta, approximately L theta, where theta is in radians. However, for small angles, sine theta is approximately equal to theta. Therefore, d equals L sin theta is approximately L theta, but L theta equals d, so for small theta, d is approximately d bar. The initial perpendicular displacement is nearly the same as the arc length of the pendulum's path from equilibrium. It follows that sin theta equals d bar over L. If you substitute this into the restoring force equation, equation 12.7, you obtain the following. Phi far equals the absolute value of mg sin theta. Far chatsu mg d yis L. Far arshimjish bash L. D 12.8. For any given pendulum, the first factor in equation 12.8 is a constant k. We have previously shown that d is approximately equal to d bar. So equation 12.8 has a form of the Hooke's law force equation, F equals kd, where k equals the absolute value of mg divided by L equals m absolute value of g divided by L. If you substitute this value for k into equation 12.6, simple harmonic motion period formula, you obtain T equals 2 pi times the square root of m divided by k, equation 12.6. T equals 2 pi times the square root of m divided by the absolute value of mg divided by L. T equals 2 pi times the square root of ml divided by m absolute value of g. T equals 2 pi times the square root of L divided by g for small amplitudes, 12.9. Therefore, for small initial displacement angles, a pendulum's motion closely approximates simple harmonic motion. Longer pendulum arms produce longer periods of swing. Pendulums appear to swing more slowly. With greater gravitational acceleration, the swing period is shorter. A pendulum swings more rapidly. The pendulum's period is not related to the mass of the pendulum, for the same reason that a heavier mass does not fall with greater acceleration than a smaller mass. Although the larger mass weighs more and has a greater force acting on it, its larger inertia neutralizes the larger weight. 12.9 Physical pendulums. Pendulums considered up to this point could be called ideal pendulums. All of their mass is concentrated at a point, and the pendulum arm is assumed to be massless. Real systems that swing as a pendulum have their mass distributed to some extent along the length of the pendulum arm. In fact, any object that can swing from a pivot point acts like a pendulum. These systems are called physical pendulums. Determining the period of physical pendulums must take into account the distribution of mass and its distance from the center of rotation. This characteristic is constant for any given pendulum and is represented by a quantity called the moment of inertia, I, of the swinging mass. A table of moments of inertia for various shaped objects is provided in Appendix F. The period of a physical pendulum has been determined experimentally to be T equals 2 pi times the square root of the product of the ratio of L to the absolute value of G and the ratio of I to ml squared, where the second factor containing the moment of inertia, I, for the physical pendulum, corrects the basic period formula for the mass distribution of the physical pendulum. When this equation is simplified, we have T equals 2 pi times the square root of I divided by the absolute value of mg times L, 12.10. Much research has gone into understanding the properties of physical pendulums, beginning with Christian Huygens, the inventor of the first pendulum-regulated clock. See Figure 12.7 on page 270. Scientists and inventors have attempted to improve the periodicity and accuracy of pendulums. The most notable of these efforts was the development of a chronometer that would withstand the rigors of the sea so that mariners could determine their longitude. Within the last century, pendulum-like devices were developed to control countless machines and activate safety systems, such as seat belts and airbags in cars. In order to understand the walking gait of people, you must know how to determine the natural period of the human leg. This knowledge directly affects the design of athletic footwear and of prosthetic limbs for amputees. The military's research into augmenting human limbs in powered combat suits also involves these principles. Learning about and using the principles of such pendulum-like systems are examples of exercising dominion over the world in ways that protect and show love to others.